4 and 5, 5 and 4.
So again, 36 possibilities, 6 high by 6 wide. Most of you guys had the first one. There's 4 that add up to 9 out of how many? 36. I'll give you guys another minute to a second to do it. A few seconds to the last one. So all the ones are bigger than 9. Not including 9. Bigger than 9. Not including 9. Do not include 9. It says greater than, not greater than or equal to. Yeah, I know. So not equal to, just greater, strictly greater than. So how many of them are there?
6.
6. 6 out of how many?
36.
6 out of 36. Good? All right. Now, complementary events. Make sure you're filling in your notes. How about Tyler? Go ahead and read for me.
The complementary events. The complement of an event E, denoted by
E bar. It has an E and a bar over it.
E bar, is the set of outcomes in the sample space that are not included in the outcomes of event E. Is everything that is not E.
Right? So the complement of E is everything that's not E. It's also sometimes written, I don't remember how your book writes it, might also write it as E with a little C in the upper corner like that, E complement. All right, so some things we know about them. The probability, if it's everything that's not E, then their probabilities of E and the probability of E's complement had better add up to 1 or 100%. Right? Because either you're one or the other. So probability of E plus the probability of its complement better equal 1. Right? Probability of E and its complement better equal 1. Which also means that if I have E and I want to find the, if I have the complement, I want to find E, 1 minus the probability of the complement should give me the probability of E. And this one comes in kind of useful. How do you get from one to the other one? You simply subtract the probability of E bar from both sides. If I did that, if I subtract it from here and subtract it from there, I would get this over here. All right, so quick question. Rita, go ahead and read for me. Great, everybody has 15 seconds to guess it. 15 seconds, think about it. Find it. I like to use change from $1, right? What'd you guys get? 77%. So 23% have vanilla as their favorite. 23%. If I buy something for 23 cents, give them $1, how much change should I get? 77 cents. So 0.77 or 77%. Right, it's the rest of them, everybody else. Those are complements. Here it is prettier. Okay. So, the probability a person does not have type AB blood. What's the probability that they have AB blood? 2 out of 50. So the probability they don't have, so I would find, there's 2 different ways you can find it. Yeah. So probability of not AB I can take these guys, add them up. 22 plus 5 plus 21 out of 50. What is that? 48 out of 50. Or I could say 1 minus the probability of AB. AB is 2 out of 50. So I do 1 minus that. I'll get 48 out of 50. Right? Because 50 minus 2 is 48. Are you good with that part? Either way. And if the fractions get you all messed up, just use your phone, your calculator, and do 1 minus 2 over 50. And sorry, find 2 over 50 and then subtract that from 1. And you'll get the answer to decimal, which is totally fine as well. I don't care whether you give them to me as fractions, simplified fractions, decimals, or percents. I'm good with any of them. All right. So here's theirs. They simplified it. All right. So for now, we're going to skip this one. Do you guys have it, or did I take it out already? Oh. It looks like I took it out.
Yeah.
Okay. There's some additional rules for probability. How about Rachel? Go to read for me.
2 events are mutually exclusive events or disjoint events if they cannot occur at the same time. They have no outcomes in common. They refer to the same occurrence, same roll of the dice, same person selected, same card.
Yeah. So they're mutually exclusive or disjoint if they cannot happen at the same time. In other words, if I roll a dice, can that dice that I roll be a 4 and a 3 at the same time? No, those are mutually exclusive. Everyone on board with that part? If I pick a card, can that card be a king and a queen at the same time? No, mutually exclusive. Good? All right, so if they're mutually exclusive, then you just add their probabilities. If they're not mutually exclusive, then you add their probabilities, but then you subtract the overlap. What's something that is not mutually exclusive? Like a puppy that's a black lab and a male lab at the same time. Right? So, but you guys did those. You guys just did that. You add their probabilities and you subtracted the overlap. Right? So the probability they're a black puppy plus probability that they're a male puppy minus probability they're a black male puppy. The overlap. All right, so selecting a card. Why am I feeling like Yep, so we're skipping lab problem 5 for right now. We'll come back to it, I think. But not right now. Yeah.
Could you go back a step so we could write down the additional rules?
Yes. So I'm going to shift you guys over to the top of the next page. Lab problem number 6. I want you guys find these probabilities, and I'll give you guys a couple minutes to sort those ones out. Okay, so king or a queen or a jack. So how many, let's slide on down to our spot here. King or a queen or a jack. I have 4 kings, 4 queens, 4 jacks. So it's 4 plus 4 plus 4. Everybody on board? So that would be, where am I? So that would be 4 plus 4 plus 4 out of 52. 12 out of 52. How about a heart or a club or a heart or a spade? Well, let's see. Club or heart or spade. Club, heart, spade. There's no overlap there either. So it's also pretty straightforward. 13 plus 13 plus 13. That's 39. So 39 out of 52. Everybody good with those two parts? Now it gets a little bit tricky. Queen or a club or a diamond. Okay, so that's not as easy because we have some overlap in there. So here, if I kind of think of it, I have, the king of spades, the king of clubs, the king of hearts, and the king of diamonds. I also have the queen of diamonds, the other queens, queen of hearts, queen of spades, queen of diamonds, or clubs, sorry. But then we have all the other diamonds, right? Ace of diamonds, 2 of diamonds, 3 of diamonds, so forth and so forth. All those other guys are in there. So, how many kings are there? 4. How many queens are there? 4. How many diamonds are there? 13. But we have this one guy, right? There's one guy there that are being double counted. Is everybody with me? So it's 4 plus 13 plus 4, but I have to subtract the 2 that are overlaps out of 52. So it ends up being 19 out of 52. Did everybody get that? All right, nice. All right, so what I want us to work on next is, we'll go, well, I got a couple minutes. We're going to skip that one for now. I'll come back to that one. I want to talk about the multiplication rules and conditional probability. 2 events, A and B, are independent events, and the fact that A occurs does not affect the probability of B occurring. 2 events, A and B, are independent events. So this is on your notes right here. And the fact that A occurs does not affect the probability of B occurring. And it has to do with changes in probability. So I'm going to talk about that a little bit. Oops. Today, before we move on. So here, quick question. Does drawing a heart give you any information about whether or not it's a king? I have a deck of cards. I draw a card. Oops. I've drawn a heart. Does that give you any information about whether or not it's a king?
Well, it's not a king.
Could be a king.
Well, you drew a heart.
I drew a heart. It could be.
Oh, yeah.
It could be any one of those,
Oh, it's
right?
1 out of 13 that it's a king.
It's still 1 out of 13 chance of being a king. So, what's the probability I draw a king normally? What's
4 out of 52.
Yeah, probably king is 4 out of 52, which simplifies to 1 out of 13. Now, if I know it's a heart, now it's a probability that I draw a king. So probability of king given, this line here means given, this line straight up, given it's a heart. So given it's a heart, now it's our probability that's a king. 1 out of 13. 1 out of 13. Everyone see that? That 1 out of 13. Is everybody with me in this part? Okay. So that's 1 out of 13. Have these probabilities changed? This one to that one, are they the same or different? Same. So it is independent. The probability doesn't change. It gives you no information at all. Knowing it's a heart does not change your probability, so heart and king are independent of each other. Does that everyone understand what what I'm saying? Because it doesn't matter whether it's a heart or not. It's still 1 out of 13. It's independent of it. Okay, that's the definition. The probabilities don't change. Now, I'm going to change the situation. Here's my king of hearts. Everyone see my king of hearts? Everyone see it? I'm going to throw it out. Now, I'm drawing a card. Oh, the card I've drawn is a heart. Does that change the probability to king? Yes. What's the probability to king? 0. The king of hearts is right there. So then it becomes dependent. Does everyone understand what I'm saying? Whoops. Because the probability of king is 3 out of 51 after I remove the king. So it simplifies down to 1 out of 17. The probability of king, given it's a heart, is 0, just like you guys said. So everybody with me? So that makes it dependent. Because knowing it's a heart gives you information about whether or not it's a king. It changes the probability. You don't have to change it completely to 0, but if changed it. Okay. Let's try something else. I'm going to take 5 cards. Ace through 5. Good? I'm going to mix them up. Draw a card. What's the probability she draws an ace? Okay, so here are the 5 cards. Ace through 5. What's the probability that she draws an ace? 100%? What? 1 out of 5. Draw a card. Okay, put it back. Now, should we put it back? What's the probability she draws an ace? Same thing, but if I draw it, don't look at it. Hang on to it. Now, what's the probability that he draws an ace? It depends, right? There's 4 cards left. She drew a card. What's the probability he draws an ace? 1 out of 4 or 0 out of 4, depending upon what she drew. Does that make sense? The probabilities are not the same anymore. They're different. Go and draw a card if you want. So that's dependent. Do you guys? So if you have it, if it's with replacement, it's independent. The probabilities stay the same. If it's without replacement, then the probabilities are dependent. So that applies generally to the stuff we're going to be doing when we have balls or cards or whatever. We draw them without replacement or with replacement. Okay. I think that is probably enough for today. All right, I will see you guys on Wednesday. Have a good day. Tuesday. I'll see you guys tomorrow. Don't come Wednesday. Come tomorrow. Yes. Come tomorrow. Yeah, that's what someone did that. Someone actually